So welcome to this last session of the morning. I am very happy to chair this session and to introduce Gabriel for his paper, which is entitled Optimal Space Lower Bound for Deterministic Self-Stabilizing Leader Election Algorithm, and who has been awarded the Best Student Paper Award. So let us enjoy your talk, Gabriel. Thank you.
Thank you. So, good morning, everyone. I'm Gabriel Le Bouder, PhD student in Sorbonne Université, and this is a joint work with Lélia Blin and Laurent Feuilloley. We introduce an optimal space lower bound for a large variety of deterministic self-stabilizing algorithms, and especially for the leader election problem. So minimizing the space complexity of algorithms is especially interesting in networks in which devices have small memory or small battery. A good example of such networks is wireless sensor networks. Since devices have small battery and or small memory, it might be important to, it might be crucial to make them communicate with, make them exchange as few signals as possible. So another property of such networks is the fact that they are wireless, and so faults in the exchange of messages may occur, which means that algorithms designed for such networks should be fault tolerant. The fact that fault-tolerant algorithms have to communicate, make devices communicate even after the solution has converged, confirms the fact that we would like to find optimal algorithms with few memory exchange. Another consequence of the wireless property of those devices, of those networks, is the fact that what we call the many-to-many communication. In such networks, when a device wants to communicate with another one, for example, if the car wants to communicate with the truck, the message is sent to all the neighbors of the car, all the neighbors nearby, which means that it's it's a problem to solve how to send a message to one specific neighbor. From the reverse point of view, when the truck receives a message, it does not know a priori if the message was sent by the car or by the bus on the right. So both those problems might be overcome. For example, the car may say, I am the car and I want to communicate with the truck, then the message, but this requires more information in the messages, and we want messages as short as possible. So classically, we model the networks with a non-oriented connected graph with n nodes. We suppose that the graph is identified, so each node has a globally unique ID, but we do not suppose that those IDs are consecutive. We suppose that they are in a polynomial range in terms of n, so identities are distributed in between 1 and n to the c, where c is any constant greater than 1. And we call delta or delta of g the degree of the graph. Edges represent the fact that nodes may communicate, so when 4 wants to communicate, the information is sent to all the neighbors of 4, and from the reverse point of view, nodes receive the information of all their neighbors. So in our model, nodes have two types of memory. The immutable memory that is non-corruptible and non-updatable by the node. Typically, it contains the code of the algorithm, the port numbers, or the unique ID of the node. On the contrary, the mutable memory is corruptible, is updatable by the node, and it contains the variables used by the code, by the algorithm, and we call the set of the mutable memory of the variables is called the state of the node. Communication between nodes only takes place in the mutable memory. So, for example, if a node wants to communicate its ID to the other node, it has to store it in the mutable memory first, but then it becomes corruptible and it takes place. So since the communication takes place with the mutable memory, we consider as the space complexity of an algorithm the quantity of bits necessary required by the algorithm on each node. So let's detail how the communication works. So repeatedly, nodes execute atomically the following action. So it reads the states of all the neighbors. Deterministically, it computes the new state that depends on the ID, its own state, and the state of the neighbors. And then it updates its own state. So recall that when a node wants to communicate with the neighbors, the same information is sent to all the neighbors, which is the state of the node itself. So it's a bit challenging to be able to make two nodes communicate just within each other. But for some problems, we have to do that kind of thing. For example, to construct a tree or a spanning tree, or to pass a token, you have to make nodes communicate one with one another. Depending on the model, this can or cannot be done with an additional cost. So the first line, the preliminary remark that the IDs can be stocked in log n bits. So if the network is identified to make nodes communicate one with each other, we can use the ID. For example, if 4 wants to communicate with 5, it can say as a prefix of the message, I am 4, I want to communicate with 5, and this is the message. So this has a cost of at least log n in the size of the mutable memory used. Another least powerful model is the port known model, in which nodes have use channels to communicate with each other and know on which channel the reciprocal nodes communicate with them. So we can do things in this model too. And the least powerful model is the anonymous, in which nodes have no information that allows us to distinguish or to be distinguished by their neighbors. So we have that there exists impossibility results in a lot of impossibility results in the anonymous model. In the following, we consider the identified model. So we consider self-stabilizing algorithms as they were introduced by Shrestha in 1974. So an algorithm is self-stabilizing if the two properties hold. Once from any configuration of the system eventually reaches a correct configuration according to some specification depending on the problem we want to solve. And the other property is that once the system is in a correct configuration, then it does not reach an incorrect configuration. So these algorithms are useful for systems that are prone to faults. Indeed, if a fault in red occurs, then we have the guarantee that the system will eventually reaches a new reaches correct configurations. So one additional property we could hope for self-stabilizing algorithms is the silence property, which is the same, but once in a correct configuration, then the system stops moving, and it does not. Yeah. So this require that how to say, the fact that a stable system can be activated as soon as one error occurred implies that nodes can locally detect if a configuration is or not a correct configuration. So we focus on the leader election problem, which is a fundamental problem since it might help to construct spanning tree or things. So for the silent self-stabilizing algorithm, the complexity of leader election is pretty well known. In 1994-99, Dolev, Gouda, and Schneider proved that leader election and some other problems could not be solved without at least log n bits per edge. And in 1994, Aurora and Gouda introduced a self-stabilizing, silent self-stabilizing algorithm for the leader election that costs exactly O of log n bits on each node. Actually, for silent self-stabilizing algorithms, we have tools that allows us to have proofs on complexities. Proof labeling schemes were introduced yesterday by Laurent and Dana, I think. A tool that is useful so for that, because we know that if there exists a silent self-stabilizing algorithm, then there also exists a proof labeling scheme by definition. And so, yeah, introduced by Corman, Couton, and Peleg. And in 2014, Blin, Freitas, and Petr proved that a kind of reciproc of that property, that which means that we can obtain lower bounds and upper bounds on silent self-stabilization only by focusing on proof labeling schemes. Yet, the more general case of self-stabilization is much well known. The only existing lower bound was introduced in 1999 by Bocchier, Gradinario, and Jonen. They proved that the leader election cannot be solved with a constant number of bits per node. And on the opposite side, in 2018, Blin and Ittai provides algorithms for both leader election and spanning tree construction that require log n plus log delta bits per node. So our problem was to fill the gap between the lower bound and the upper bound for the general case of leader election. So we did. Our main theorem proved that if there exists a deterministic self-stabilizing algorithm for a problem for P that use less than log n over delta bits per node, then the same problem can be solved on one family of graphs by anonymous algorithms. So by algorithms that do not use the ID. This allows us to use the impossibility results that were developed prove for the anonymous model. One corollary of that theorem is since leader election is known unsolvable even on rings, anonymous rings, so with delta equals 2, this theorem allows us to say that leader election cannot be solved with registers of size less than log n bits per node. So I'm just going to give you a brief idea of the proof of that. So we consider a ring within nodes. So nodes have identities between 1 and n to the c greater than 1. And we consider an algorithm that uses f of n bits per node. So nodes have two neighbors. 4 has 15 and 7 as the neighbors. So we can consider that the algorithm is a function that maps the ID of the node, so 4, and 3 strings of bits of length f of n. So this is the input of the algorithm, and the output of the algorithm is a new state for the node, so a string of bits of length f of n. So the main idea is to consider that there is not one algorithm that takes as input the ID of the node, but to say that there is as much algorithms as there exist IDs. In a sense, we hardcode the specificity of the ID into the algorithm, which provides several algorithms. So we don't know if there is as many algorithms as there exist IDs. For example, if the algorithm only uses the parity of the ID, so you only have 2 different new algorithms. So we don't know exactly how many such algorithms exist, but we can find an upper bound on how many algorithms, because it's easy to compute the size of the set of the functions from 0, 1, 3 f of n to 0, 1 f of n. So this is the maximum number of hard-coded algorithms, 2 to the f of n multiplied by 2 to the 3 f of n. So f of n appears at the second level of exponent. So this number grows fast with the f of n. But if f of n is small enough, so maybe we can have a result. And indeed, as soon as f of n is smaller than log n, then we can prove that the number of hard-coded functions is smaller than n to the c minus 1. That's why we needed c greater than 1. And as soon as there are much fewer functions than there exist IDs, the Dirichlet drawers principle allows us to say that you can always find at least n different IDs that are all mapped to the same hard-coded function, here delta 2. And then, if you select on your n node ring those at least n IDs, then you have an anonymous algorithm, since the hard-coded effect of the ID is the same for all the selected nodes. And thus you cannot break any symmetry, you cannot, for example, you cannot perform a leader election or construct spanning tree or anything like that. So that's it. So we introduced a theorem that links the algorithms with a small memory complexity and on the one hand and on the other hand anonymous algorithms. And this allows us to introduce a new lower bound for the leader election problem. And one work that is still to do is to refine a bit more this, since the existing algorithms uses an additional log delta bits to solve the leader election. So is it necessary to use log delta bits for that problem? Thank you.
So the second talk will be given by Luciano Freitas de Souza, and the paper is entitled Accountability and Reconfiguration, Self-Healing Lattice Agreement.
Good morning, everybody. I'm happy to present to you our paper, which builds on the keynote from Petr, and it was written by myself, Luciano, Petr, Thibault, Rieutord, and Sara Tucci-Piergiovanni. So as Petr said, it's very important in distributed system to know how to deal with failures. And I'd like to introduce one analogy that from real life to our systems, where fault tolerance is like a lock you put in the door, and accountability is like a camera. So the lock in our doors will prevent people from breaking in, and the camera will raise evidence that someone did something. So one solution prevents, and the other brings the people who did malicious behavior into the justice. And again, the costs of each of these solutions, the classic one of fault tolerance is replication and synchronization. And in the case of accountability, we need to consider the cost of signatures and the fact that we have to maintain histories to understand the behavior of the different processes in the system. So the options we have in dealing with the evidence is, of course, to go to the judiciary system. We can make stake slashing, such as in Tezos, where you confiscate money from people in the blockchains. And our solution is about replacing misbehaving parts with new parts in the hopes that we'll eventually converge to a system where the processes are correct. So, yeah, the first solution that might come up to mind is indeed to use consensus. But the thing is, consensus cannot be solved in asynchronous systems, and it has a linear latency lower bound for it. And if we, in the case we use Lattice agreement, not only we can provide solutions to asynchronous systems, we can also provide solutions in logarithmic time. So the idea is to interpret the configuration of the system as a lattice by having this set of the replicas and by appending a plus or a minus in a pair, so to indicate that the replica was included or excluded. So if you have in the last line, for example, a set with S1, S2, and with pluses and no minuses, then they are included in the configuration. But if you see some replicas which have plus and minus, then they are excluded from the configuration. So a natural question is, yeah, we've been talking about how to deal with the configuration of our system, but of course our system must do something. And what can it do? So there is a result which was presented by Laurent that indeed Lattice agreement implements a specific subset of state machine replication. So if you have a problem and you can split all operations between updates and reads, that meaning that you either modify the value of a variable or you read the value, and the updates are commutative, then you can interpret your data structure as being a lattice object. So examples include sets, counters, storage systems, and possibly cryptocurrencies. And the good thing is that because when we compose a lattice with another lattice, we get a new lattice, we can use one configuration lattice for our problems and then change the object lattice to fit to the specific application. So going to the lattice agreement with accountability and reconfiguration, how does the system operate? So first of all, it's an asynchronous system. So we don't have any bounds on the time that messages take to arrive. And the processes, they will exchange values in the composed lattice. So we have processes that will at the same time communicate configuration and object. And this actually is a very good feature, because if you have a solution which has decoupled configuration and object, once you change a configuration, you need to go through extra steps to transfer the information that was in one configuration to the new one. But because we deal with the composed lattice, we get it for free, because once the object is updated, the configuration is already updated. So we have clients who propose values to the system, which is maintained by replicas, and they propose it in a sequence of values, and they learn a sequence of values as a result. And not only they learn values, they also maintain an accusation set. So an accusation set is a set of pairs where you have on the first element a process, and in the second element you have a set of messages. So the idea is that this set of messages contain signatures, and together they contain proof enough that some object has equivocated. For example, you can see that an object has acknowledged a value v, and then it acknowledged a value w, which is not comparable to v. And then in the long-lived solution, we assume that the clients are benign, but these can also, we still can deal with Byzantine clients. So the idea is we have to choose, and this is something which is not yet stabilized, where the configurations come from. So for example, some previous work have considered that you have a pool of replicas, and then you somehow get a new pool of new replicas to work from this pool. But here we're being more realistic, and we're supposing that the client chooses some replicas in the system. So in a sense, you could, for example, think of a system where you have administrators who choose the configuration, and then you would have some degree of trust there. And then you have clients who can be Byzantine and do anything they want. Or on the other hand, you can have some sort of access control mechanism, so you prevent, for example, a Byzantine from proposing a configuration which completely splits the system and makes it impossible to merge it again. And one of the nice features that we get is that we can actually provide a solution which tolerates, in some sense, what I mean by tolerate here, in fact, it maintains properties for a majority of correct processes. Because normally in these systems you would have to have at least 2/3 of correct processes. And here we only have a simple majority for a given configuration. So we have a set of properties that we've designed, and the idea is to make a new properties which match the existing Lattice agreement problems. So as the classic Lattice agreement, we still have validity. So the idea is that the values you learn is a join of the values you have already learned and values which come from other clients. But perhaps the most important thing here is completeness. Because in the case of completeness, what we require is that if processes learn incomparable values, they will eventually accuse someone from being Byzantine. And because we're dealing with lattices, it's very easy to later to merge once you detect that this happened. In fact, you only have to join the state of the system. Then we have this notion of accusation stability, meaning that once you accuse someone, you won't forget that you accused them, and your accusation set will only grow. We have accuracy, so if a process is correct, it cannot be accused. We have authenticity, meaning that you cannot forge proofs saying that some correct process is Byzantine. And then we have agreement. But here it's agreement on the sense that if I accuse someone, then eventually everybody will accuse this process. And finally, we have liveness. And the way we define liveness is that if someone includes a value in the system, eventually all processes will learn a value which includes this value introduced, assuming that the process who introduced the value is correct. So now, we can think about how the system works. So we have clients who are exchanging values with the replicas, and they maintain the object states and configuration states they are passing through. And the replicas, they issue either an acknowledgement or a NAK if they accept or not the value. And the idea is that the processes are trying to collect sufficiently enough acknowledgements to learn a value, and they use the NAKs to update their proposals so that they eventually learn a value. And if you're familiar to the classical generalized lattice agreement, it's the same solution. But then we have introduced some very important key differences. So the first difference is that normally we only care about values and not where they come from. But because we are dealing with accountability, we have to check all the time and keep track of the origin of these values. And then, because we're essentially running a crash fault tolerant system with Byzantine processes, of course, there will be some safety violations. So you'll have to keep check, for example, when you decide a value, you must propagate it to the system, and the other processes, they will eventually raise an accusation based in your decision value, for example. And once you're working with a stable system, a static system, it's easy to know when you should stop. Whenever you reach a majority in your configuration, you can learn your value. But here, first, we assume that the configurations, they are being rapidly exchanged. And if you learn a majority of, if you get a majority of responses on the current configuration, it might not be enough. Because it might be that due to the synchrony, some other processes have different views of the current configuration, or they might have already learned new values, which brings them to new configurations. So we had to introduce this notion of pending configurations. And the idea is that we can define a set of configurations such that if you get a majority, if you get responses that form a majority in all of these sets, then you can learn your value. And then we have a very important problem, which is due to the asynchrony, a client might have an outdated view of the system. And then they might try to communicate with a replica which has been corrupted. And the replica can pretend that they're still in the system when they have already been removed from it. So in order to prevent this, we use this cryptographic primitive, which is called forward secure signatures. So the idea is that you have one public key and you have a set of private keys. And as you go through the system, you move in this sequence of private keys and you destroy the old ones. So the key has, in this case, must match the configuration. So essentially, by seeing the signature of a process, you can see that they're trying to pretend they are in a configuration when their signature indicates that the configuration has already moved forward. So you won't accept this value coming from them. So what's then it's left to do in this case? Well, as we said, accountability requires processes to keep very large histories of the system so they can check the behavior of the replicas. But the problem is, if you want to discard something, you don't necessarily know when it's safe to discard values. So essentially, the data that you're gathering is growing from the beginning of the system. So it's still an open problem how to deal with garbage collection and how to safely cut the history without losing the accountability. And then in this first paper we presented, we based on linear versions of lattice agreement, but then it's also interesting to see if we can have logarithmic solutions with accountability. So I hope that my talk sparked some interest in you to read the paper, and I thank you for your interest.
Okay, so now we are welcoming the third paper with William Schultz. He will present us the design and analysis of a logless dynamic reconfiguration protocol.
Hello, my name is Will Schultz. I'm a PhD student at Northeastern University in Boston, Massachusetts. And today I'm going to present our work about the development of a logless dynamic reconfiguration protocol in the context of the MongoDB replication system. I'm advised at Northeastern by Professor Stavros Tripakis, and this work was to a large extent originally completed by myself and a former colleague at MongoDB, Siyuan Zhou. So I'll just start by motivating what area we're working on here and what kind of problem we're solving. So as has been discussed previously, the Paxos and Raft consensus protocols are now ubiquitous as underlying and serving as the rigorous foundation for most modern fault-tolerant data storage and data replication systems. And to be resilient to failures over time, these systems must be able to add and remove nodes via dynamic reconfiguration. Right? For example, if you want to elastically scale up or down your cluster, or even if you want to just perform a software version upgrade or something like this, you want you to be able to dynamically reconfigure the system over time. But creating new dynamic reconfiguration protocols is not always so easy. It can be somewhat of a challenging problem to develop these protocols from scratch. They're generally subtle and hard to get right. And as an example, the Raft, one of the original Raft proposals for reconfiguration, which they termed their simpler single server change approach, had a bug that was discovered, a safety bug that was discovered only after the initial publication, and there was not included a full correctness proof of that protocol originally, or a formal specification either. So MongoDB is a distributed database with a replication system that conceptually derives from Raft in many ways, with some extensions and modifications, but under the underlying protocol is very similar to Raft. And replicated databases in MongoDB run in what we call replica sets, which are just simply sets of servers that act as a consensus group. So following this classic state machine replication model, where there's a single leader or primary that's elected, that leads that drives the replication process and replicates entries to servers that each apply them in a consistent order. So since the inception of MongoDB, it included a mechanism, a legacy mechanism, so-called, for doing dynamic reconfiguration, but and this mechanism was logless, we term it, in the sense that reconfiguration first was decoupled from the main database operation log. So it was a protocol that ran to some extent concurrently and separate from the main state machine replication log. And no log of reconfigurations was explicitly stored. So every server had a local configuration, and these were propagated in a gossip-like manner, but there was no replication log or anything managing configurations. And this allowed for kind of a simple and a clean and modular design. That the protocol was relatively simple architecturally and was decoupled from the rest of the state machine replication machinery. But the problem was that this legacy protocol sort of worked well enough for clients in common cases, but it was easy to construct scenarios where this protocol was unsafe and would lead to safety violations, like, for example, the key, basically one of the key safety properties, that if you acknowledge to a client that a write is durable or committed in the replica set, then it should be present in the future. Right? So the problem that this work centers around, which is what we worked on at MongoDB, was that we needed a new safe dynamic reconfiguration protocol for the MongoDB system with these sort of engineering design constraints. So first, of course, we wanted to be able to make this protocol correct in a formal way and have some kind of rigorous safety guarantees. But we also wanted to try to minimize the changes to this legacy logless reconfiguration architecture to the extent possible. From an engineering standpoint, this was we wanted to simplify our design as much as possible if it could be done. So this paper really centers around this contribution, which is a new protocol we call MongoRaft Reconfig, which is a reconfiguration protocol that's satisfying these design constraints. And to summarize the contributions of this work in a bit more detail, so we present this protocol called Mongo Raft Reconfig, which is a so-called logless dynamic reconfiguration protocol that in some ways can be seen as a generalization or an optimization of aspects of Raft's single server reconfiguration approach. We also include a safety proof for this protocol, which to our knowledge was the first published safety proof for a Raft-based reconfiguration protocol. We also have a formal specification of the protocol in TLA Plus and present results of model checking the safety properties of it on finite instances of the protocol. And then we also do a preliminary experimental evaluation where we look at potential performance benefits of this reconfiguration approach, having to do with how it decouples reconfiguration from the main database operation log. Okay, so with that, I'll talk a little bit more about the protocol itself in detail. So as I alluded to before, many replication protocols may take this approach where they handle reconfigurations by putting special log entries into the main database operation log. Okay, so you have this classic state machine replication model again, where the system is, your database, for example, is modeled, let's say, as a key value store, and operations on your log update the replicated state of this object, this conceptual object, right? And you put maybe regular data updates into that log, as well as configuration updates, which have maybe special semantics or a different behavior, but you put everything into the same log. So conceptually, or in terms of the architecture, Mongo Raft Reconfig decouples the reconfiguration processing from the main operation log, and then it also makes it logless, okay? So which I'll explain in a second. So you have a state machine replication log for the standard database, let's say like your key value store, with operations on logical user data. And then conceptually, you have a separate replicated state machine that just deals with configuration. And then the protocol sort of goes further, and you can think about the configuration subprotocol as conceptually a state machine replication log, but it then sort of goes further and optimizes away this log and only stores the latest object, because configurations really are this update only operation, so you're able to optimize away this log, and that's how this protocol works. At least this gives a conceptual overview of the architecture of the protocol. So a little bit more formally, in this Mongo Raft reconfig, a configuration is defined as a tuple MVT, where M is what we call a member set, which is simply a subset of all the possible servers that might be in the system over time. V is a numeric configuration version, and T is a numeric configuration term, which is the term value that's borrowed from, if you're familiar with Raft, is borrowed from that aspect of the protocol. So each server in a replica set then maintains a single copy of this, a durable copy of a configuration. And furthermore, configurations are then totally ordered by their version and term pairing, okay, where term is compared first and then version. And this ordering is somewhat analogous to how log entries are ordered and compared in the Raft algorithm. So as a concrete example, this is a possible system state for a replica set with 3 servers, at least in terms of what the configuration state could look like on different nodes. So N1 and N3 think that the configuration consists of N1 and N2, and then N2 thinks that everybody is in the configuration. But N1 and N3 have like a newer configuration based on their version and term. So the fundamental, or the most important sort of behavior of this protocol is doing a reconfiguration, the most important operation. So we say that a reconfiguration on a server S from C to C prime will update the local configuration of that server S. And there's some restrictions on this. That first, it can only occur on a primary server. Okay, so as in Raft, there will be a leader that accepts writes, and reconfigurations can only occur on that leader server. And it also requires this quorum overlap property between these adjacent configurations. So, like in most of these Paxos or Raft based algorithms, you use quorums, right, to write something durably that then you ensure is read later by some later server that accesses a quorum of servers. this quorum overlap property says that for adjacent configurations, any quorum of one will intersect any quorum of the other, right? But in general, if you're doing reconfiguration over time, you may have an arbitrary set of configurations that you move through, so you can't guarantee this property globally in time, but you do ensure it locally between adjacent configurations, which is like a concept that's sort of adapted and similarly appears in some of the raft reconfiguration approaches, where you have this restriction on how you can move between adjacent configurations. And then there are additional preconditions that you must satisfy before a reconfiguration can occur. So conceptually, these preconditions must ensure two sort of essential aspects of doing reconfiguration safely, which are referred to as deactivation and state transfer. So if you think about the system conceptually, just simplifying a bit as moving through a sequence of configurations over time, you may have at any one time some set of configurations that are, in a sense, active or activated. It's noted here by the green coloring. And as you move through configurations over time, you need to make sure that basically if two configurations couldn't safely operate concurrently, that one of them gets deactivated, essentially, that it can no longer, for example, elect a leader or commit rights. So as you move forward through configurations, these old configurations indicated in red must be deactivated. So for example, if you look at C1 and C3 here, if you just do the basic majority quorum, for example, electing a leader using a quorum, there are quorums of C3 like N2 and N3, majority quorums of C3 like N2, N3, which will not intersect any server of a majority quorum of C1. And then there's additionally this issue of state transfer, which is that if, for example, let's say you write data durably to a quorum of servers in one configuration, you need to make sure that that data is propagated to quorums of future configurations. For example, if you commit a write on a quorum of servers, that somehow needs to be propagated forward to quorums of future configurations so that future servers know about that information. So making those conceptual safety preconditions a little more concrete, there are three, which I won't describe formally, but I'll describe the high-level idea of the preconditions that must be satisfied before you can execute a reconfiguration. So the first is what we call a config quorum check, which says that there must be a quorum of servers in your current configuration that have installed that configuration. And this, coupled with the ordering rules like configuration, essentially ensures proper deactivation of old configurations. We also require this term quorum check, which says that there must be a quorum of servers in your own configuration that are at your current term, the term of the primary executing the reconfiguration. And this has to do additionally with state transfer of term information through configurations. And then finally, this oplog commitment rule, which says that log entries committed in terms older than your own must now be committed on a quorum of your configuration. So if they were committed in an older configuration, they're now committed by the rules of your current configuration. So that's all I'll say formally about the protocol at this point. So I'll switch to discussing additional efforts that we did surrounding this work and part of our contributions, which is doing having a formal specification and model checking the safety of the protocol. So the protocol is formally specified in TLA+, which is a specification language that's was originally developed by Leslie Lamport and is suited generally for concurrent modeling, concurrent and distributed protocols. The complete specification is around 400 lines of TLA+, and it's at a relatively high level of abstraction, which we found both sort of useful for communicating the essential behaviors of the protocol and also for making automated verification more feasible. So to give you a sense, I won't go through the whole specification, but just to give you a sense of what the protocol looks like in TLA+, you, for example, define the state variables of your system. Here, showing the state variables that relate specifically to the reconfiguration behavior. And then you define your system simply as a set of initial states, basically as a state machine where you define a set of initial states and a transition relation that defines how the system can transition between states. And your overall system specification is a conjunction of these two things. It's specified as a single logical formula. And to dive a little deeper, then we can just see, for example, how we would formally express things like the quorum overlap property, which just is basically defined as saying for between two sets of servers X and Y, for all quorums in one and all quorums in the other, the intersection of those two sets must be non-empty. And then we also have the formal definitions of these preconditions, which I discussed informally before. And then, for example, can see how a reconfiguration operation is defined as a so-called action in TLA+, where we have preconditions which are predicates over the current state of the system, and so-called postconditions, which are indicated here with the primed version of the variables, which say what should the value of a variable be in the next state of the system. So our model checking efforts consisted of checking safety properties of finite instances of Mongo Raft reconfig for up to 4 servers using this TLC model checker, which was a tool developed for TLA plus specifications. The scalability of this was somewhat limited, so we also took an approach where we independently verified properties of the reconfiguration subprotocol, which had sort of interesting safety properties on its own to verify. And just to give you a rough sense of this type of verification effort, these are some statistics about what we verified. So for the overall protocol, our finite model looks at systems with 4 servers, and where the terms and number of configurations that can occur, for example, are bounded to some finite size. And this produces a state space of like around 300 million states running with 20 parallelized workers. And it completes in like roughly about 8 hours or so. And then we also did an additional effort which looks at the reconfiguration sub-protocol, which is sort of a subcomponent of the overall protocol. And we're able to look at larger instances. So this is with 5 servers and up to 4, maximum number of configurations of 4, and a larger state space of 800 and so million states in about 20 hours. Okay, so finally, I'll speak briefly about our experimental evaluation, which you can find more details about in the paper, but generally, we look at the potential benefits of decoupling reconfigurations from the main operation log as compared to standard raft. So there are certain situations that we test in our experiment where, for example, you can do a reconfiguration because you are able to like commit things in these two conceptually different logs independently without forcing everything to go through a single log. So if one of the logs, for example, is slow or bottlenecked, you can bypass it in certain situations, and this helps you reconfigure away unhealthy nodes. And I'll leave the details of that experiment to the paper, but that gives a general idea. So now I'll wrap up with some final conclusions on this work. So as I said, this Mongo Raft reconfig is this new logless dynamic reconfiguration protocol. And really the concepts, though we sort of developed them in the context of MongoDB and this replication protocol, they should be generalizable to replication systems that are based on Raft and perhaps even other replication systems as well. In terms of some additional work, so the full version of the paper is available on arXiv, and since the completion of this work, we've also worked on writing a formal inductive invariant for safety in TLA plus and writing a machine-checked proof using something called the TLA plus proof system, which allows us to write a proof that can be automatically verified by a computer. And that work will appear in a few months at the CPP 2022 conference. And then you can also see the specifications at this link to see the formal TLA plus specification of the protocol. Okay, so thanks.
So the last talk will be given by Nibesh Shrestha, but he will be online, and it's a pre-recorded presentation.
Hello everyone, this is Nibesh. So I'll be presenting our work on the good case latency of rotating leader synchronous BFT. This is joint work with Ittai and Kartik. So to briefly motivate our work, synchronous BFT protocols are generally favored for the higher fault tolerance as they tolerate up to 1/2 Byzantine failures. However, synchronous BFT protocols depend on the pessimistic network delay big delta for their safety and liveness. An important metric in the study of these protocols is the latency to commit a decision. And for synchronous protocols, the latency to commit a decision depends on the pessimistic network delay big delta, which is usually much larger compared to the actual network delay small delta. Recent work have improved the latency of synchronous consensus protocols under the stable leader paradigm. In particular, they improved the good case latency, which is the latency to commit a decision under an honest leader. And a recent work designed optimal latency BFT protocol with a good case commit latency of 1 big delta plus 1 small delta. The focus of this work is to study the good case latency of synchronous BFT protocol in the rotating leader setting. Most prior BFT protocols focus on the stable leader approach, where a single replica takes lead in coordinating all participating replicas into reaching consensus. In general, stable leader protocols provide better performance both in terms of throughput and latency, as they avoid a view change process to switch leaders, which incurs additional latency. Prior works on synchronous BFT protocols, they have designed protocols to optimize the latency to commit under an honest leader. For example, Synchronous has a good case commit latency of 2 big delta plus 1 small delta, and optimal latency BFT has a good case latency of 1 big delta plus 1 small delta. An important property of both of these protocols is that these protocols can progress at network speed, although commit depends on the big delta. However, protocols on the in the stable leader approach lack support for fairness and censorship resistance. Another line of work focuses on the rotating leader approach, which provides better support for fairness, censorship resistance, and uniform distribution of work. Indeed, many BFT protocols have been designed with this goal in mind. For example, Hotstuff, Tendermint, and Casper. Assuming synchrony, few recent works include Definity, Pili, and Streamlit have been proposed. However, these protocols incur large latency to commit a decision. In particular, Pili requires 65 big delta to commit a decision, and Streamlit requires 12 big delta to commit a decision. In addition, these protocols require a sequence of good leaders to commit a decision. Alternatively, we could also use the state-of-the-art stable leader protocols in the rotating leader setting. However, these protocols inherently contain a synchronous wait during the view change phase. For example, a sync hotstuff incurs at least 1 big delta during view change phase, and optimal latency BFT incurs at least 2 big delta time during the view change, although these protocols have a very good case latency. Thus, these protocols cannot make progress at network speed in the rotating leader setting. So in the rotating leader setting, the leader is changed after every proposal. Thus, the view change is mandatory after every proposal, and the overall latency depends on the sum of good case latency to commit a decision and the latency of view change. One natural way to reduce the overall latency is to reduce the view change latency, that is, change leaders and allow new leaders to propose in order small delta time. We call such protocols as optimistically responsive rotating leader protocol. An optimistically responsive rotating leader protocol allows a protocol to progress at network speed, as the next leader can propose immediately after receiving input from the previous leader. In this work, we study the good case latency of such optimistically responsive rotating leader BFT protocols. Before discussing more on rotating leader protocols, let me present a common paradigm that is adopted by many recent works. Our protocol follows the block chaining paradigm, where a leader proposes a value in the form of a block, say block bk, which explicitly extends a block bk-1 proposed by an earlier leader by including hash of the previous block bk-1. And this block bk-1 is the parent of block bk. And the blocks from its parent up to the genesis is in the same blockchain are called its ancestors. In this paradigm, when a block bk is committed, all its ancestors are also committed, and all blocks in the log up to block bk can be safely used. In addition, when the leader of block bk is honest, block bk and all its ancestors can be committed with a small constant latency in the good case. So in the context of optimistically responsive rotating leader BFT protocol and blockchaining paradigm, the key question we asked in this paper is, what is the optimal good case latency of an optimistically responsive rotating leader chained BFT protocol? So to answer this question, we first formulate this problem as a rotating standard chain reliable broadcast. In the rotating standard chain reliable broadcast, there is a sequence of designated senders P1 through Pk such that P of I broadcasts a block B of x at height x with following properties. The first property is correctness. That is, if an honest party delivers or commits a block B of x at height x, then all honest parties eventually commit or deliver block B of x at height x. The next property is validity, where if an honest party or honest sender P of I broadcasts B of x at height x, then every honest party eventually delivers B of x at height x. Next, we have extension property. If an honest party P delivers block B of x at height x, it delivers all the ancestors of block B of x. This property captures the protocols that follow the block chaining paradigm, where if a block is committed, all its ancestors are also committed. The final property we have is sequentiality, where if an honest sender P of I proposes a block B of x at height x, it must extend block Bx prime proposed by earlier honest sender P of j. This property ensures that honest parties do not propose blocks that extend arbitrary blocks and ensure validity for blocks proposed by prior honest senders. Given this definition of rotating sender chain reliable broadcast, we formally define optimistically responsive rotating sender chain reliable broadcast as follows. In an optimistically responsive rotating sender chain reliable broadcast, given two consecutive honest senders P of I and P of I plus 1, Pi plus 1 sends its input or block proposal in O small delta time after receiving P of I's input or block proposal. And our lower bound is formulated in terms of optimistically responsive rotating sender chain reliable broadcast. We answer our main question on the good case latency of optimistically responsive rotating sender reliable broadcast by our lower bound. Our lower bound is for a generalized Wheatstone latency alpha, where alpha ranges from 0 to delta. Our lower bound says that even in an optimistically responsive rotating sender chain reliable broadcast tolerating a minority corruption, if the Wheatstone latency is alpha, then there exists an execution where the following two conditions do not hold simultaneously, where the good case commit latency is less than 2 big delta minus of alpha time. And the next condition is honest senders broadcast responsively in at most alpha time after receiving an input from the previous honest sender. That is, honest senders propose in an optimistically responsive manner in at most alpha time. So the crux of this lower bound is that if the sum of commit latency and the Wheatstone latency is less than 2 big delta, then there can exist executions where different honest parties can commit different values at same log position, and it can violate the consistency property. Next, I will briefly present our lower bound at a high level. We consider an algorithm A whose good case commit latency is less than 2 big delta minus alpha, and the Wheatstone latency is at most alpha time. In the lower bound proof, we show a sequence of walls and through an indistinguishability argument show a correctness violation. For simplicity, we assume the number of parties is n equals to 2f plus 1, and the parties are partitioned into 3 sets: set P containing f parties, set Q containing f parties, and set R containing only one party. In world 1, parties in P and R are honest, while parties in Q have crashed. Since up to f parties can be faulty, this is within the allowed fault threshold. Parties in P and R start at time 0, and an honest sender S1 that belongs to set R sends a block BK to all parties, and message exchange between parties in P and R arrive instantaneously. Since the sender is honest and our good case commit latency is less than 2 big delta minus of alpha, parties in P commit block BK before time 2 big delta minus of alpha time. In world 2, parties in Q and R are honest while parties in P have crashed. And parties in Q and R start at time 0. An honest sender S1 that belongs to set R sends block B prime K to all other parties, and message exchange between parties in Q and R arrive instantaneously. The next sender S2 that belongs to set Q receives B prime K at time 0, and by the sequentiality property, the next sender sends S2 extends B prime K and sends value BK plus of 1 by time alpha. Since the sender S2 is honest, by the validity property, parties in Q and R eventually commit BK plus of 1, and by extension, parties in Q and R commit B prime K. So world 2 shifted is a shifted version of world 2, shifted by delta minus of alpha time. In world 2, parties in Q and R are honest, while parties in P have crashed. And all parties start at time delta minus of alpha. An honest sender S1 that belongs to set R sends value B prime K to all parties, and message exchange between parties in Q and R arrive instantaneously. Note that honest parties do not take different actions even if they start after delta time. Thus, the next sender S2 sends value bk plus of 1 by extending b prime k with a view change latency of alpha time, that is by time delta. This execution is identical to world 2. Thus, parties in Q eventually commit bk plus of 1, and by extension, parties in Q also commit b prime k. Finally, we have the hybrid world. In this world, parties in R are Byzantine and all other parties are honest. Parties in P start at time 0 while parties in Q start at time delta minus of alpha. The Byzantine sender S1 sends value bk to parties in P and value b prime k to parties in Q. Parties in P receives the sender's value at time 0 while parties in Q receive the sender's value at time delta minus of alpha. Parties in R behave like world 1 towards parties in P and behave like world 2 shifted towards parties in Q. And messages between parties and P and R arrive instantaneously, like in world 1. Similarly, parties in R sends messages only to parties in Q only at time delta minus of alpha, and messages between Q and R arrive instantaneously, like in world 2 shifted. And messages exchange between parties in P and Q is delayed by delta time. In world 1, parties in P start at time 0 and message exchange with parties in R arrive instantaneously. Since parties in Q are crashed, parties in P do not receive any messages from parties in Q. Similarly, in world hybrid, parties in P start at time 0 and message exchange with parties in R arrive instantaneously, where parties in R behave identical to world 1 for parties in P. Moreover, since parties in Q start at time delta minus of alpha and message exchange between parties in P and Q are delayed by delta time. Thus, parties in P do not receive any messages from parties in Q until 2 big delta minus of alpha time. This implies parties in P cannot distinguish between world 1 and world hybrid until 2 big delta minus of alpha time. Hence, parties in P commit BK before 2 big delta minus of alpha time. Similarly, in world 2 shifted, parties in Q start at time delta minus of alpha and message exchange with parties in R arrive instantaneously. Since parties in P are crashed in world 2 shifted, parties in Q receive no messages from parties in P. In world hybrid, parties in Q start at time delta minus of alpha and parties in R send messages only at time delta minus of alpha and messages between R and Q arrive instantaneously. Observe that parties in R start at time 0 and messages between Q and P are delayed by delta time. Thus, parties in Q receive no messages from parties in P until time delta. And parties in Q cannot distinguish between world 2 shifted and world hybrid until delta time. Hence, the next sender that belongs to Q sends value bk plus 1 by extending b prime k sent by the Byzantine sender by delta time. By the bilaterality property, parties in Q commit bk plus of 1 and by extension also commits bk. Thus, we have a correctness violation at height k. Thus, we conclude that the sum of commit latency and the view change latency has to be at least 2 big delta time. Next, we present an upper bound protocol. We give a rotating leader BFT SMR protocol with a good case commit latency of 2 big delta and a view change latency of order small delta. This protocol is optimal as the sum of commit latency and the view change latency is 2 big delta, ignoring order small delta time. And this is optimal due to our lower bound. Our upper bound protocol follows similar design as the state-of-the-art sync R-stop protocol, which is a stable leader protocol. So in our protocol, replicas move to higher view as soon as they receive a certificate for a block proposed by previous leader. When they enter a view V, they set a view timer to 7 big delta and start counting down. And the new leader proposes block BK by extending previous block BK minus of 1 as soon as it receives a certificate for block BK minus 1. That is, as soon as it enters view V. And replicas simply forward the proposed block and vote for the first valid proposal. Again, replicas move to higher view V plus of 1 as soon as they receive a certificate for block BK. Committing a block BK happens in the hindsight in the non-blocking manner. Replicas commit block BK only when they receive a certificate for block BK, such that there is still sufficient time in VUV, and commits in 2 big delta time if no bad behavior is detected from the leader of block BK. For full protocol specification and security analysis, please refer to our paper. So in our protocol, the new leader proposes a block as soon as it receives a certificate for the block proposed by earlier leader. In general, certificates can be received at network speed. Thus, the new leader proposes responsibly and the protocol makes progress at actual network speed. Committing of the proposed block happens in the hindsight in the non-blocking manner. Hence, given a sequence of k honest leaders, our protocol can commit k blocks in 2 big delta plus order k small delta time as shown in the diagram. And the sync out stuff, which is a stable leader protocol, also commits k blocks in 2 big delta plus order k small delta under an honest leader. Thus, our protocol can be viewed as a rotating leader version of sync out stuff. So we implemented our protocol and compared it with stable leader, state-of-the-art stable leader protocol sync out stuff. In our implementation, the leaders are rotated in a round-robin manner. In terms of latency, our protocol obtains latency comparable to sync out stuff and matches the latency profile we discussed in the earlier slide. However, sync out stuff has much better throughput compared to our protocol. And this is because the performance of sync out stuff depends on the F+1 fastest replicas in the system. And being a stable leader protocol, the leader can schedule block proposal as soon as it has proposed previous block. In contrast, the performance of our protocol depends on the slowest replica in the system due to the round-robin leader rotation. Moreover, a leader can only schedule a block proposal after it has been elected as a leader. In addition, the new leader has to perform some additional computation as it needs to deduplicate the proposed commands, as commands may arrive in different order and different replicas. So although this stable leader sync out stuff provides better throughput, it is worth to note that stable leader approach doesn't provide fairness and censorship resistance. We also compared the performance of our protocol against the sync out stuff protocol in the rotating leader setting, so that even the sync out stuff provide fairness and censorship resistance. However, this modified version of sync out stuff contains synchronous wait during the view change, and because of this, both its throughput and latency suffers, and our protocol performs better. So to conclude, we gave a lower bound on the good case latency of optimistically responsive rotating leader synchronous BFT protocol and provided an upper bound protocol with an optimal good case latency. Thanks for your attention.